In this tutorial, we want to analyze a very simple truss under 2-point loads. One horizontal point load acting on this joint B and one vertical downward point load acting on joint D. The truss is supported by a hinge and a roller. And we consider that the truss is weightless, so we're not considering any cross-section for this truss. Now, let's move to rhino and grasshopper. The first step to analyze the truss is drafting of the truss itself by just simply drawing every single element as separate lines, okay, like this. So these are just drafted as lines. Now, to transfer this geometry to grasshopper, I'm going to drag and drop a geometry component onto the canvas, and then select set multiple geometries, and then select the entire geometry, hit enter. Let's make sure I selected everything. Okay. When I hover over it, it says 5 elements are defined. Okay, wonderful. Now we're going to get started with Karamba. The first component we're going to drop onto the canvas is a sample model. Will let us accumulate the information about elements, supports, loads. And then the next one is create linear elements. So it lets us define the truss as linear elements that can get analyzed, because Karamba by itself doesn't understand lines as beams or columns. And then the next set of components are supports. I'm going to drop one support component and I'm going to duplicate it, because one will be a hinge, one will be a roller. A hinge, as we discussed in the previous tutorials, will be defined by restricting all translational movements. And here in this case that I drafted the truss in X, the Z plane, I'm going to restrict rotation about X and rotation about Z, but rotation is allowed about Y axis. For a roller, actually translational movement along X can be allowed, but not along Y or Z. Also, rotation about X and Z should be restricted, but rotation about Y can be allowed. Then I'm going to call list item to define at which of these joints I'm going to place a hinge at which a roller. So index 0 will give me this point. So I'm going to connect it to this hinge support. And then list item. I'm going to connect points to the list. And pick, I think, index 2. Yes, there we go. So as I mentioned in the previous tutorials, this index value might be different for you based on how you drafted and in which order you drafted your truss. Now I'm going to connect both supports by holding the shift button on the keyboard. And I'm going to flatten both elements and supports, and later I'm going to flatten the loads. Now here we're all set with the supports. Now in the next step, I'm going to define the loads. So I'm going to pick loads, and we're going to have 2 point loads. And both of them are concentrated loads. I'm going to give it a name like F1 and define the vector. So first I'm going to define the horizontal vector. And the horizontal vector was positive 2 kilopounds, which means that the 2 kilopounds, it's along the X direction. So I'm going to call unit X to define the direction. and drop a panel and give a magnitude of 2 to that vector. Now I should define, oh, here it seems that everything got duplicated here as well. So we'll just get rid of these extra. Oh, come on. Extra elements. For some reason, it got duplicated. Okay, now I'm going to connect the elements. Oh, first of all, I'm going to drag and drop list item. And I'm going to connect the list of the elements, means the list of the beams that I have, the list of the members that I have. And then I will try index 0 to apply the point load to that element. And I'm going to pick the orientation as global so that the X will be along the X axis. And I'm going to connect load to the load input on the assembly model. To view the point load, I'm going to go to the results, model view, and connect model to model. So here I see that the horizontal point load is applied to the wrong element. So I'm going to try the other one. Index 1 will be this one. 2 is this one. Well, actually, this is good. This is this element. And now I can move this point by defining the right T position to this end. So I'm going to define the T position, which is either it's number 0 or 1, depending on how you drafted your model. Either of these two will be correct. So 0 will bring the point load here. So I'm going to put 1 here. And there we are. This is this position. One good way to see which element you're going to pick is to drop a panel, connect the elements to it. Here, read the specification of the beams. Here is index 0 is a beam from 000 to 3600, which is this element. Now, the one that we connected, beam index 2 is 3600, like 3600 to 36027, which is here, this one. And here we are. Now we need to define the next point load. This time I'm going to delete unit X because the point load is along the Z direction. Now I'm going to connect it to the point of application, load case, now is F2. And then T position 1, now I'm going to call unit Z. And the magnitude was 5. I'm going to connect it to the force vector here. And then I'm going to connect this load case to assemble model as well by holding the shift. Now here I'm still seeing F1. I should go to the result selection, pick F2. So here, I should correct this definition. So first of all, orientation should be global. And this time, this should be -5 because 5 means it's upward. And then I would like to apply this point load to this joint. So I will click 0. There we are. So now we have 2. Now Karamba considers these 2 point loads separately to analyze the beam. So we should define a load combination. Now I go to load case combination, and load case combinator here. I'm going to give it a name, FT, which means F total is the name of the load case. And now the definition of FT. So FT equals F1 plus F2. Make sure you're consistent with uppercase and lowercase letters. There we go. And now what I'm going to do, I'm going to hold the shift and connect both of these to the load input as well. Now here, another load case as FT is popping up. There we go. We're all set with the model that we want to analyze. Now it's time to use analyze component under algorithm dropdown list and connect model to model and analyze model to model. Wonderful. Now we can see the deformation and I can check the reactions to be able to see the reactions under both load cases. So you can play around with the display scale of deformation and reactions. It doesn't affect the magnitude of the reaction. And in order to see the forces and truss members, we're going to drag and drop beam view and connect the model from model view to here. Now I open up these two drop-down lists, check off cross section, and then I want to look at the normal X, which means the axial forces, and I will click on field and numbers. So I want to see the field diagram and the numbers. On the front view, I'm going to see the axial forces and increase the display scale. So the force in the vertical web member is 5. And here in these two bottom elements, both members are under tension because they're in color blue, and 4.33 is the value of the tensile force in them. I mentioned this in my previous tutorial, but I will repeat it here. So make sure you connect the model from model view to beam view, because here you could select the load combination FT. If you connect the analyze model to beam view, then you will get much lower axial forces because the default load case for analysis for display here is F1, not FT. Okay, so connect the model view to the view to get the right combination of the loads. And we'll turn this off to see everything better. And there you go. You have all the axial forces in the truss that you designed.